Those pictures you see are a visual representation of unstable behavior generated by a very simple rule. Well, not literally. What those really are the tangent lines to the graph of a special sequence of polynomials, whenever they cross the y equals x line. In this video, you will understand what does this have to do with instability, and also why a lot of those lines are parallel. And believe me, the reasoning behind this will get you into a whole new level of appreciation by a concept you already use all the time, that of conjugation. This idea of taking a problem, bringing to a world where it is easier to solve, and hopefully bring something meaningful back. Consider the function that takes a number x between 0 and 1 and sends it to 4 times x times 1 minus x. The first thing you might notice is that the number you get is still between 0 and 1, so you can apply the function again, and you'll never leave the interval. In other words, that means that the composition of G with itself, or the second iterate, is still a function from the interval 0, 1 to itself, and so is all of the nth iterates. We'll call them Gn for short, and the sequence of values obtained for a particular initial point we'll call an orbit. Now, if just randomly taking values and calculating the output again and again sounds tedious, I got a fun, purely visual challenge to you. Pause this video and guess in which of these intervals, L or R, lies the second iterate of this point. And as a tip, I'm gonna draw the y equals x line, but feel free to use whatever method you come up with. Give it a try. The key idea here is that the horizontal and vertical axes actually represent the same thing, the possible positions or states of your system. The graph helps you by telling what is the state one iterate ahead, given your current. All you have to do is bring it back to the original axis, and you do that by projecting the height into the y equals x line, and out to the same value in the x-axis, where you can apply the process again. Alright, now what if I asked you where is the 100th iterate of the same point? Well, this method actually only takes you so far. So a natural question that might arise is, where do these orbits go? I mean, I know they keep inside the interval, but do they have a preferred region where they like to spend time in? It turns out this question is actually hard when you're talking about this particular function. So we'll dial it back in complexity to one we can understand well, by just replacing this 4 by a 2.5. Doing our y equals x drawing for the randomly chosen point, we don't need to do 100 of them to start seeing the pattern. Almost every initial condition converges to the value 0.6, which itself stays in place. Those points are called fixed points. Their dynamics is the simplest possible. I mean, they stay in place. We can't ask for more predictability than that. Though both 0 and 0.6 are fixed, there's a fundamental difference between the two. The point 0.6 not only stays in place, but also attracts all of its nearby points, while the point 0 doesn't seem to like its neighbors too much. The first case is called an attractor, and the second one, a repeller. There's a pretty simple criteria to distinguish these two cases, involving the derivative at the fixed point, or the slope of the graph at the crossing with the y equals x line. You ready? Compute the derivative at the fixed point and take its absolute value. If it's bigger than 1, it's a repeller. If it's smaller than 1, it's an attractor. The proof of this involves how the iterates either stretches or contracts distances based on the derivative. But for now, I encourage you to think for a minute and convince yourself of why this is true by looking at those graphs. This quantity that dictates the dynamics of your neighbors is called the multiplier of the fixed point, and is going to be the crucial concept we're going to dive in for the rest of the video. What's the next simplest behavior after standing still? To see that, let's increase a bit more the complexity, moving this parameter up to 3.2. Notice we still have the two fixed points, like in our previous example, but now both of them are repellers. What happens then? Well, pick another point and let the function decide. And there's our next simplest behavior right there, oscillation between two values. This is called a periodic orbit, with period 2. Is there a similar notion of multiplier acting here? You might say, well, now it's not that clear since there's no y equals x line intersecting the graph in order to compare slopes. Oh, but there is if you look at the second iterate of g. It turns out a period 2 point is nothing more than a fixed point of g2, which happens not to be a fixed point for g. More than that, it is easy to convince yourself that the convergence happens in g if and only if it happens in g2 for one of the points. And since now we're analyzing the attractiveness of a fixed point, there's our multiplier right there, just the derivative of g2 at one of the points of the orbit. But which one? A simple computation using the chain rule shows it doesn't matter. If g2 is just g composed with g and x1, x2 are the period 2 points, the chain rule gives us g2 prime of x1 is g prime evaluated at g of x1 times g prime of x1. But that's just the derivative applied at both points of the orbit multiplied. Inverting the order and noticing g sends x2 back to x1, we arrive at precisely g2 prime of x2. Oh, and to make it just right, we're going to have to average it out, taking the square root, since the speed of convergence is twice as fast if we're looking at g2. Take some time to convince yourself that the same argument works for orbits of any period. Alright, now we're ready to get into our spooky initial example. If you start plotting the iterates of 4x1 minus x, you'll convince yourself very quickly that the periodic points keep showing up, no matter how high is the period. The question we're going to answer is, are any of those attracting? What do you think? Pause here and take a guess. You might argue that in the other examples it took just a couple of periodic orbits to quickly find one that attracts everybody, except for the other ones. So here, with fixed points showing up non-stop, some of them will certainly happen to cross the y equals x line at a slope that's less than 1. On the other hand, since the other ones are also growing out of control, you might say there's maybe nothing left to attract, as if somehow their competition left them all empty-handed. We're going to try to answer this question using the idea of multipliers. I know there's infinitely many orbits, but let's just calculate the first low period ones in order to build intuition. And as a side note, I should say that the payoff here will be pretty good. Remember, the criteria is simply to check whether the multiplier is bigger or less than 1, and we need to do only one per orbit. Okay, the fixed points are clearly not attracting, since the derivative here is 4 and negative 2. Now we're going to rely on some numerical computations. The multiplier in the period 2 case is the derivative of g2 at one of the period 2 points, taking the square root. And we get something very close to 2 again. Let's do one more. For the period 3, we have 2 orbits. Let's choose this point for the first one, and this for the second one. We seem to always get values close to 2. Well, this pattern is begging to be generalized, except here there's not a clear way of seeing it holding true for higher periods. Try to ponder about how unlikely it actually is for that pattern to keep persisting. It involves taking all of the solutions of a 2 to the n degree polynomial equation, which may contain many different orbits, applying the derivative of the same monstrous polynomial, taking the nth root, and checking it equals 2 every time. Oh, and doing it for every n. Here's where the main character enters. What would be a map where this question is simple? The answer? Just flatten out everything you can. The result is something like this function, which we call the tent. It has slope 2 and negative 2 everywhere except at 0.5. Therefore, any periodic orbit that doesn't contain 0.5 has 2 as multiplier. But 0.5 itself cannot be part of a periodic orbit, since in 2 iterates it settles in the fixed point 0, never returning. So, rephrasing it, any periodic orbit has 2 as multiplier. In order to prove this has any connection with the 4x1 minus x function, other than similar looks, we'll need a bridge between the smooth polynomial world and this flat, piecewise linear one. And this bridge is, surprisingly enough, a trigonometric function. Consider the function c of x equals 1 minus cosine of pi x over 2, where our inputs will be taken in the interval 0, 1. This is a smooth one-to-one correspondence from the interval 0, 1 to itself. It also satisfies this relation, g equals c of t of c to the minus 1. Whenever a map satisfies this, we call it a conjugacy. In this case, this can be proven by using some simple trigonometric identities, but don't bother with the details. In fact, once we establish those properties, you don't have to bother with the function at all. And here's why. Suppose all I told you is that there exists a differentiable one-to-one function called c, which satisfies this relation. What could you work from that? Well, the meaning of this is that instead of calculating g, we can move over to the 10th word via c, calculate t, and come back, and we're going to get the same result. More strongly, c also works a conjugacy between gn and tn for any iterate n, meaning instead of iterating g, say, 20 times, we can move over, do all the 20 iterations in t, and come back. So, vaguely speaking, conjugation creates a bridge between two otherwise distinct worlds. What can you transport over that bridge? As a first consequence, notice that periodic points of g are taken into periodic points of t. But the main question is, does c transport multipliers? To answer that, and make sure we don't need anything else from c, the chain rule will make its final appearance. Take any periodic point of g, call it x. Call n its period. Then, x is a fixed point of gn, and the multiplier is given by the derivative of gn at x. How to calculate that? At first we have no idea, we don't even know what x is. But we know, once we move to the 10th word, its twin, c minus 1 of x, which we're going to call y, is also a periodic point, has same period, and has 2 as multiplier. The last thing we'll need from c is the fact that its derivative vanishes only at the fixed point 0. And so for the following, we're going to throw out this exception. Now, rearranging the equation to ctn equals gn of c, we have ctn prime of y equals gn of c prime of y. The chain rule gives us that. But y is a fixed point of tn, so the terms involving c cancel out, giving us that tn prime of y is gn prime of x. But we know tn prime of y is 2 to the n, since y has 2 as multiplier. Therefore, the multiplier of the orbit of x is 2, where x can have period 2, 3, or 3000, doesn't matter. In particular, that means that for this function, the multiplier is the same not only inside a particular orbit, which has to happen anyway, but also through all of the orbits. Visually speaking, the slope of any fixed point of gn, with 0 as the only exception, will be 2 to the n, as highlighted at the beginning of the video. The reason I find this example particularly elucidating is that here conjugation is a concrete object, a function from the interval to itself with some smoothness properties, and it's actually the main character of the story. It takes in an impossible task, that of solving arbitrarily large degree equations, computing the derivative, taking the nth root and checking it equals 2 every time, to an absolutely trivial one, multiplying 2 together n times and taking the nth root, paying the price of creating a smooth bridge and understanding the chain rule, which means you can transport multipliers over it. So, my hope with this video is that you think about the power of conjugation next time you're diagonalizing a matrix, doing a change of variables in your integral, or I dare to say even outside math, when you're watching a cool magic trick or listening to a really investing and finally rewarding story. And realize that all of that comes from the same place.